The previous video introduced the concept of capillarity and the two fundamental parameters, which is what happens at the interface between two immiscible fluids, which is the surface tension, and what happens when these two immiscible fluids interact with the third one, the substrate, and now they form a contact angle as the balance between the three interfacial tensions. And then we show that contact angle and interfacial tension give rise to a whole series of phenomena, from capillary pressure, the Laplace equation, capillary rise, the contact angle and interfacial tension, and then we continued hinting as to potential implications in soils. Today we would like to explore this further, and let's start by one additional observation. When we say that we have an interface between two immiscible fluids, what we are actually saying is that this is at the state of equilibrium, when fluid A has reached the saturation into fluid B and vice versa. That, for example, being the case of oil and water, or CO2 and water. What about the case of air and water, which is the more common case in soils? Well, the same happens. If this is the water level and this is air, then water molecules, which are dipoles, I'm not going to draw them completely, are continuously jumping out, and actually air now contains water molecules at a lower density than in the liquid, of course, because it's a vapor phase, but these ones are also continuously jumping in. In other words, it's not static equilibrium, it's an ongoing jumping in and jumping out, and when the system reaches equilibrium, the bombardment of the water molecules in vapor onto the liquid phase is what we call the vapor pressure. Now, there are several immediate consequences of this dynamic situation. One is that air and water are continuously in exchange. And so there are air components that dissolve in water and water that becomes vapor in air. And we could have the following situation: container with water, and of course, if we wait long enough, it will vaporize. However, if we take the container in water and we place a cover on top, then the water molecules will jump in and out until we have enough vapor pressure that the system is at equilibrium and evaporation stops. So the one on the left will dry out, the one on the right, some will evaporate into the cavity, and then evaporation will stop when the system reaches equilibrium. There is another consequence of that. If we have our clothes drying and the wind is blowing, then the vapor that forms around the clothes is taken away by the air, and this helps the clothes dry. Clearly, if we would have put the clothes inside the container and sealed them, evaporation would eventually stop, and they will remain for the most part wet. If the day is very still and there is no wind, it takes some time, but if the wind is blowing, evaporation will happen much faster, because the air takes away the water cloud that forms around the clothes. There is another consequence of this, and it is related to the effect of curvature and vapor pressure. So if we have, let's consider the following capillary tubes. The ones on the right are going to be non-wetting, and so a water droplet, if we fill it up, a water droplet will form a convex geometry, the same here. But in this case, if these are water wet, actually we're going to have a capillary rise. according to the Laplace equation. So this would have been zero curvature. This is positive curvature, and this is negative curvature, because we measure it from the inside, and here we have to measure it from the outside. Now, if we have such a system in an enclosed space, so it is in total equilibrium, what we would observe is that the water would evaporate from the small one into the large one, and from the convex ones into the concave in this cascade. In other words, these tubes are communicating, they are talking through the vapor pressure. In fact, there is a relationship that connects the vapor pressure to the vapor pressure under saturated conditions at equilibrium, to the capillary pressure, which we call delta U, which is U air minus U water, which by Laplace is equal to the liquid vapor interfacial tension over the radius. In fact, would be 2 radius. And so this is actually a proportionality, and there are a couple of constants that remain in this psychrometric law. But this is very important because menisci are talking, and the goal is to effectively get to equalize the vapor pressure. The same happens when you have a crystal, and if you had a small crystal and a large crystal, and we wait long enough in an enclosed system, the large crystal grows at the expense of the small crystal, and this is called Ostwald ripening. So this happens with crystals, and crystallization tends to concentrate on large crystals. The same happens with the vapor pressure, and the communication is taking place the same as in crystals. This communication is taking place through diffusion. In other words, the molecules that are here are vibrating, and they're jumping in, and eventually are finding their way into systems with decreasing vapor pressure. These fundamental concepts are going to help us understand what happens inside the soil, and by the way, also they help us understand the interaction between the soil and the atmosphere. Let's explore next the evolution of saturation as suction increases. Imagine that we have a soil mass. We are running the test in the space shuttle, and at the beginning it's all surrounded by a bubble of water, and then gradually we begin to dry the water until menisci begin forming between particles. Please realize that the curvature of these menisci is related to the capillary pressure by Laplace, and also related to the vapor pressure, which, by the way, is the relative humidity. And so all these curvatures should be exactly the same. I haven't done the drawing very well. For example, this curvature, the radius of curvature is smaller than in this case. So this is not a good sketch. Please draw things properly, because the sketches we draw affect the way we think. So once again, let me bring this particle closer so I can draw a higher curvature to properly reflect the situation. As you can see, now the pressure of the air is greater than the pressure of the water. The water is put under tension by these menisci. And there is something else that happens. These menisci, the negative pressure and the tensile membrane, which is the interfacial tension pulling around this perimeter, is bringing particles together. So this is going to cause contraction, as we will soon review. But at this point, even if this was a cemented sand and it was very stiff, at this point you begin to see that I'm already beginning to invade the volume, just with the menisci, and so the degree of saturation is beginning to decrease as the suction increases and the curvature increases, But at some point, the radius cannot get any smaller before it actually jumps and invades into the soil skeleton to form new radii of curvature. And once again, the whole thing gets balanced, equalizing the negative pressure through the water, the continuous water phase. At this point, where I invade the skeleton, we're going to call this the capillary pressure at air entry. That is a very important point, and it's going to be controlled by the largest exposed pore in the soil, because that is where the interface will enter first. Thereafter, the system will continue drying, and menisci will continue invading, reflecting which is the largest pore that comes next, and the weight of the soil and of water in the soil and the degree is decreasing, while the degree of saturation is decreasing as well. And so this will follow something like this. And I made a tail here because at the end, probably there are very small pores. So this is a typical capillary saturation curve, which in geotechnical engineering we often refer to the soil-water characteristic curve. It follows from this analysis that if we had a fine-grained soil, the pores are smaller, and because of Laplace, the suction required to invade them is inversely proportional to the pore size. Therefore, they will require higher suction. So this would be the saturation capillary curve for a fine-grained soil, homogeneous. This would be for a coarse-grained soil, homogeneous. So this is coarse, I'm exaggerating. This is fine-grained. And if it was a mixture of coarse-grained soil and fine-grained soils, so air would invade according to the large pores in the coarse, but then as the water remains only within the fine-grained elements, then it will follow this line and it will go to that line. And so this is a mix. Please notice that I could turn these curves around and they would look like the grain size distribution. So this would be, if I plot cumulative percent passing versus grain size, this would be the grain size distribution for a coarse soil, for a fine-grained soil, and this is the mixture. So this is the coarse, this is the fine, and this is the mix. So recognize that this is almost a rotation. You see the grain size distribution, and you can begin inferring the shape of the soil-water characteristic curve. There are other things that occur in this lower end where we tend to see the tail going up. Any fines that were floating in the system are going to migrate with the water, and they're going to concentrate, aggregate, probably flocculate near the contacts of the large grains. And so at this point, probably we have particles and we have fine grains coming and accumulating near the contacts of the coarse grains, and this is what the loess is. You can see some SEM images of loess, and you see these fine-grained abutments that accumulate near the coarse grains, helping the stability of loess under high suction conditions. And if you also continue drying, all the water that remains probably has too much salts, and the salts are going to begin precipitating. So at the very end here, you may see some crystals of salt, soluble salts that precipitate near contacts. So there will be fines migration, crystal precipitation, and so even in homogeneous sands, but if you pull them out from nature where there may be some fine particles and salt, you are going to see these tails toward the very end of the drying. If you follow the discussion that we have had, now we can anticipate other phenomena. As you begin drying the soil, it gets to a point that the water remains only at menisci. And therefore, the water phase is not a continuous phase anymore. And we're going to call that the soil-water percolation, the water percolation in soils, the percolation threshold. That means that if the water is not continuous anymore in this lower end, all the communication between the water and menisci will happen through the vapor pressure. While in this regime, all the communication and the homogenization of pressures is happening through the continuous water phase. Now, we can do the opposite argument. Imagine that we start with a perfectly dry soil and we begin filling it up with water. At the beginning, the air was a totally continuous phase, but at some point, air is not forming a continuous phase anymore. There may be ganglia or areas where air remains trapped, but is not communicating. And so we can identify another percolation threshold, which is the percolation threshold for air. Now, it follows from this discussion that if I plot the permeability of water, the permeability of water will be very high when the soil is 100% saturated, but it will go to 0 when I am at the water percolation threshold. So the permeability of water in an unsaturated soil increases like that. And just to be able to compare with the permeability of air, let me plot here the permeability of water with respect to the permeability of water at 100% saturation, and this value is going to be 1.0. Now, the opposite happens for air. When it's perfectly dry, I have 100% air conductivity. However, when I reach the percolation threshold of air, then it cannot be transported anymore. So it looks something like this. So this is what we call the relative permeability for water, and this will be the relative permeability for air, where what I'm actually doing is the permeability to air divided the permeability to air at 0% saturation, water saturation. This has very important implications because, for example, if I'm trying to pull oil out of a reservoir and then water begins invading the reservoir, I may do a water flooding, there is a fairly high percentage of oil that I will never be able to remove because it remains trapped. And in this case, I'm showing it that it remains trapped in menisci, but it gets more complex because the formations are always heterogeneous, and so big ganglia may remain trapped in lenses of finer sediments where it is difficult to penetrate them with the invading phase. Let's go back and reanalyze the case that we covered during the video on effective stress. Imagine that I have a saturated formation and that there is an anticline so that I'm able to inject a light fluid inside the anticline until I fill it up. This could be gas, this could be water, could be air. At the interface, the air and water, I could say, or the oil and water, let's say that this is oil and water. At the interface between oil and water, the two of them share the same pressure. The outside, the pressure increases with depth, the pressure of the water. Inside, beneath the anticline, the pressure of the oil recovers, but proportional to the unit weight. In other words, the mass density of oil times G, while here is following the mass density of water times G. Therefore, now there is a difference between the water pressure and the oil pressure, even inside the anticline, because, as we showed before, this is not just filled with oil, it's filled with oil and water. The oil invaded and displaced the water, but the displacement was proportional to the soil-water characteristic curve, proportional to this capillary saturation curve. Now, at every point, I can compute the difference in pressure between oil and water, which is this quantity here, This is the delta pressure, and based on that delta pressure, I can go to the characteristic curve, and for that formation, and I can determine what is the soil, the water saturation versus depth within this formation. Clearly, the higher I go, the higher the capillary pressure, the difference between the two pressures, the lower the water saturation and the higher the oil saturation. By the way, this curve falls under the name of Van Genuchen. In the geotechnical field, in the oil field, they fall under Brooks, Corey. They are very similar expressions and basically describe the same capillarity versus saturation curve. So consider this as our first example. Let's go to another situation which happens when we take specimens from the bottom of the ocean or from a deep water. So this is the sediment, and now we are going to recover this specimen and take it to the surface for analysis. Now, because of bioactivity and trapped gases, the water here is saturated with gas. It's basically like club soda or Coca-Cola. You don't see the bubbles. There are no bubbles that you can see explicitly, but it's saturated with gas. Now, when you remove the pressure to bring it to the surface, all the bubbles are going to come out of, the gas is going to come out of solution and form bubbles. In the case of Coca-Cola, the bubbles form and emerge to the surface, but what happens in the soil? Well, imagine that we have the grains, and as a bubble nucleates somewhere here on the surface, it's going to grow and it's going to displace the water, but the water likes the soil, so it's wetting it, and so it forms menisci, all of them with the same curvature. And probably in this case, I will have to make the particle larger, otherwise I will not be able to enclose it. And so here are the menisci that is forming, and so now all this is the gas phase. And so there is desaturation, but not coming from the outside, is desaturation coming from the inside by gas nucleation. Now, this gas now has higher pressure than the water. You see the menisci are constraining it. And so the particles experience two things. Experience the gas pressure greater than the water, which is pushing them out, and the menisci that are grabbing the particles, and the interfacial tension is also pushing them out. So these particles are being pushed out away from the gas bubble, which means that by the time we take this specimen to the surface, it's going to be significantly destructured. In fact, many samples, particularly the finer grains, by the time you get them to the surface, they have so many bubbles that they look very similar to chocolate mousse, a very foamy structure where the grains are floating in bubbles. Massive destructuring, and so we have to think, how can we sample without ever depressurizing the system? And the technology to do that is called pressure core technology. The next example explores once again what happens when the sediment dries, something that we started talking about in our previous video. And so imagine that I have a water surface here, and I have a sediment, and now the water begins evaporating. And if I measure the weight, and this could be a specimen in a container, if I measure the weight, of course, I'm going to see that the weight decreases rapidly until I hit the water surface, and then water is going to continue evaporating. If I zoom in now at this point when the water reaches the surface, then I have the grains and the water meniscus at the surface. Now, once again, this puts the water in tension, And so the lower part of these particles experience the suction compared to the upper part. Furthermore, they also have the interfacial tension pulling them down, and so every particle wants to go down. And this produces self-compaction, consolidation of this sediment, driven by the suction of the drying soil. Now, remember that all these curvatures have to be the same because the negative pressure is communicating through the liquid phase, which is still continuous. So if we take it one step further in the drying process, now I'm going to get to a point that menisci are curved here, but that curvature cannot be sustained there anymore because there is a large pore, and now the meniscus invades the sediment and forms this interface. If I analyze the forces, look, this particle is being pulled down, this one is being pulled down, down, this one is down, down, this one is sideways, and of course this one is sideways. And this lateral pull-out is going to enlarge the pores, and because the pore gets enlarged, the meniscus invades even further and further, and that leads to what we call a desiccation crack. I insist, I am assuming absolutely no tensile strength in this material. Desiccation crack, for the most part, is primarily the invasion of the air-water interface through the largest pores into a soil. In fact, if we go back and look at this container carefully, very likely this container will show a desiccation crack that forms peripherally around the wall first before other desiccation cracks. Why? Because the pores near an interface tend to be larger than in the soil, so these side walls are the ones that are invaded first, and we tend to see that extensively in experimental studies. Now, the suction that is developing in the soil inside here lowers the water pressure. The water pressure decreases, gas may come out of solution, and if gas comes out of solution, grains inside here may also be pulled apart by the expanding air bubble, and internal desiccation cracks periodically form in soils. And we have been able to observe them using micro-CT, putting soils that are drying inside the micro-CT, and you see how bubbles nucleate and begin pulling the soil out, and while fractures are happening at the surface, internal fractures are also developing.